In this video, we will be looking at section 4 of chapter 12, the integrated rate law. Remember previously we looked at the differential rate law, which shows how the rate of a reaction depends on concentrations. With the integrated rate law, we will show how concentrations depend on time. Here are the learning targets, where we will be looking at concentration versus time data to determine the rate law, and we'll also be looking at the half-life of a reaction. So we're going to be looking at reactions that have just one reactant. And we're going to look at first order reactions first. Here's our rate law. The reactant, the single reactant, is represented here with the letter A. We can put this equation into a different form using a calculus operation known as integration, and that gives us this equation. This is called the integrated rate law for first order reactions. We take the natural log of the concentration of A at time t, and that is equal to negative K times T, so the rate constant times time. And to that we add the natural log of the initial concentration of A. This integrated rate law for first order reactions is on the AP Chemistry Equations and Constants reference sheet that you get to use on the exam. This equation is of the form y equals mx plus b. So the equation shows how the concentration of A depends on time. If you plot the natural log of the concentration of A on your y-axis and time on your x-axis, then the slope is equal to negative k, and our y-intercept is the natural log of the initial concentration of A. So for a first order reaction, whenever you plot the natural log of the concentration versus time, you should always get a straight line. So we often use this to see if the reaction is first order. So here we have some data for dinitrogen pentoxide. We've got the natural log versus time. And you can see we get a straight line. So if the dinitrogen pentoxide is your only reactant, and that's what we're talking about here, single reactant reactions, we have a first order reaction. And the slope of this line would be equal to negative k. This is the rate constant. So we can solve for the slope, and that will be our rate constant. And we know the initial concentration at time 0 for the dinitrogen pentoxide. And so then we could figure out the concentration for any time that we wanted. We could just substitute in the time and solve for our concentration of our dinitrogen pentoxide. So now let's talk about the half-life of a first order reaction. This is the time required for a reactant to reach half of its original concentration. So half-life, half concentration. This equation here is a derived equation, and you can check out your textbook for the derivation. It is based on the integrated rate law for a first order reaction equation. So here K is still the rate constant, and T would represent the half-life. So it's called T 1/2. Notice how concentration is not part of this equation. This equation is also on the AP Chemistry Equations and Constants sheet that is provided on the exam. If we know the rate constant for a reaction, then we can just substitute that in and solve for the half-life. Now let's talk about second order reactions. Here's the differential rate law, where A again is the concentration of the single reactant, and that quantity is squared because this is second order. The integrated rate law for second order reactions is here. This equation is also on the AP Chemistry equations and constants sheet that is provided on the exam. So again, we've got the concentration of a reactant A at time t. We've got our rate constant, we've got time, and we've got the initial concentration of A. This equation does not include any natural logs like the first order integrated rate law. So now if you think about this equation in terms of y equals mx plus b, we would want to plot 1 over the concentration of A on the y-axis and time on the x-axis. The slope would be equal to the rate constant k, and the y-intercept would be 1 over the concentration of A initially. So for a second order reaction, 1 over the concentration of the reactant versus time will produce a straight line. Remember, we saw a straight line for first order reactions when we plotted the natural log of the concentration versus time. But you can see for this reaction, when the natural log of the reactant is plotted versus time, we do not get a straight line. And so this is not first order, this is second order. Slope is equal to k, the rate constant, and once you know the slope, you can substitute that in. We know the initial concentration, and then you can look at any time and solve for the concentration. We also have what's called a zero order reaction. Here's the differential rate law, and the concentration of A raised to the 0 power is equal to 1. So the rate is dependent upon the rate constant. When this is integrated, we get the concentration of A is equal to negative kT plus the initial concentration of A. Again, K is the rate constant and T is time. When you think about the form, y equals mx plus b, the slope again is equal to negative k, just like in the first order rate laws. The y-intercept is the initial concentration of A, and once again we're looking at the relationship between the concentration of A and time. So this equation has no natural logs in it. It doesn't have 1 over the concentration of A in it. It's just the concentration of A equals negative kT plus the initial concentration of A. So in this graph you can see that we have the concentration of A versus time. We've got our y-intercept right here, and the slope is equal to negative k. So once you know the slope, you know the rate constant, you can substitute that in, and the initial concentration of A of course goes here, and you can substitute in any time and solve for the concentration of A. So finally, this chart nicely summarizes the different orders and the rate laws that are differential and integrated, what you have to plot on the graph to get a straight line, what the slope is equal to, and then we have half-life equations, but we are just going to worry about the first order one right here. This concludes our video on the integrated rate law.